Dear learners, in this video we will learn two theorems. One is every continuous function is bounded and another one is Bolzano's theorem or location of roots theorem. So to prove the every continuous function is bounded, we have to know the partition definition and the statement of Borel's theorem. So see, for partition of closed interval, let a comma b be a closed interval. Let a comma b be a closed interval if a is equal to, say this one a, this is b, a is equal to x naught, which is x1, which is less than x2, less than x2, and so on, less than p, which is equal to xn. Then the finite set P is equal to set of x0, x1, x2, so on xn is called a partition of a comma b. The closed intervals, this x0, x1, x1, x2, and so on xn minus 1, xn are the subintervals of the partition P. Here P is equal to set of x0, which is A, x1, x2, so on xn is equal to B. For example, let me take one example, closed interval of 1, 5. Okay, so here partition is, this is 1, 5. We can take partition as 2, 3, 4. So partition P is equal to 1, 2, 3, 4, 5. This is one partition. The partition may not be unique. There are many partitions. Let us see another partition. 1, 5, 1.5, 2, 2.5, 3, 3.5, 4, 4.5, 5. See, another partition is P is equal to 1, 1.5, 2, 2.5, 3, 3.5, 4, 4.5, 5. So this is partition 1, this is partition 2. So there may not be a partition unique, there may be many partitions. I think you understood the partition definition. So partition of a closed interval, we can partition number of partitions. Okay. So next, coming to the Borel's theorem statement. If a function f is continuous on a comma b, then for each epsilon greater than 0, there exists a partition of p of a comma b such that mod f of x1 minus f of x2 less than epsilon for x1 comma x2 belongs to IR, where IR is any subinterval of partition P. So as earlier I said that 1, 2, 3, 4, 5 is a partition. Then 1, 2, 2, 3, 3, 4, 4, 5 are subintervals. So here what that Borel's theorem states is, if f is a continuous function on a comma b, then for each epsilon greater than 0, there exists a partition P of a comma b, any partition P of a comma b, such that mod f of x1 minus f of x2 less than epsilon for x1 comma x2 belongs to IR. IR is a subinterval. These are the subintervals. So this x1, x2 belongs to any of these subintervals. That means, so IR is here, IR is xr comma xr minus 1 comma xr. That is the subinterval. So coming to the theorem statement. So what is the theorem? If A comma B is a continuous and if f is continuous on A comma B, then f is bounded on A comma B. So here already it is given that f is a continuous function on a closed interval A comma B, then we have to show that f is bounded on A comma B. Let f is continuous on A comma B. Now we have to show that f is bounded on I comma b. By Borel's theorem, for each epsilon greater than 0, there exists a partition P. There I took x0, x1, x2, so on. Here I took t0, t1, t2, so on. Tn is equal to b of A comma b. Here partition is t0, t1, t2, so on. Tn of closed interval A comma b such that mod f of x1 minus f of x2 less than epsilon for x1 comma x2 belongs to IR, where IR is the subinterval of partition P. Let us take epsilon is equal to 1. Then mod f of x1 minus f of x2 less than 1, because I took epsilon is equal to 1, for x1 comma x2 belongs to IR. Let x belongs to A comma B, and t0, t1, t2, so on tr be points lying between A and x. Then mod f of x, see here, this is A, this is B, A comma B. X belongs, suppose this is x. So the points lying between A and x are t0, t1, t2 and so on tn. We have mod f of x minus f of A. This means this f of x minus this f of A mod. Let us see what happened. Mod f of x minus f of A is equal to mod f of x minus f of tr plus f of tr minus f of tr minus 1 plus f of tr minus 1 plus so on minus f of t1 plus f of t1 minus f of A. So just I write that, I add that minus f of tr plus f of tr minus f of tr minus 1 plus f of tr minus, which will not affect the equation f of x minus f of A. See, so I took separately that mod f of x minus f of tr as one set plus f of tr minus f of tr minus 1 plus so on plus f of t minus f of A. So by we know that mod A plus B is less than or equal to mod A plus mod B. By using that, say less than or equal to mod f of x minus f of tr plus mod f of tr minus f of tr minus 1 plus so on plus mod f of t1 minus f of A. So by Borel's theorem, there we took that epsilon is equal to 1. So every term is less than 1. So 1 plus 1 plus 1 so on r plus 1 terms. So which is equal to r plus 1. For any x belongs to A comma B, there will not be more than n minus 1 points of the partition between A and x. Therefore, for all x belongs to A comma B, mod f of x minus f of A less than, where r is n minus 1 points. So n minus 1, r plus 1 means n minus 1 plus 1, which is equal to n. So from this we will get f of A minus n less than f of x less than f of A plus n. This means f of x is bounded on A comma B. Okay, coming to the next theorem. The statement is, if a function f is continuous on A comma B, and f of a comma f of b have opposite signs, then there exists c belongs to a comma b such that f of c is equal to 0. First we have to understand the statement clearly. See, so what is the statement given here? So first we have given that f is continuous on closed interval a comma b, and another one what given, f of a and f of b are in opposite sides. That means if f of a is positive, f of b is negative, because these two are in opposite side. So f of a is negative, f of b is positive. Then there exists, if these two conditions are satisfied, that is f is continuous and f of a and f of b have opposite signs, then there exists c belongs to a comma b such that f of c is equal to 0. So to prove this theorem, there are two cases. Case 1 is f of a is positive, f of b is negative. Case 2 is f of a is negative, f of b is positive. Okay, so let me give a brief introduction how I prove this theorem. See, first I took a comma b, a closed interval. The middle point I took c, that is c is equal to a plus b by 2. If f of c is equal to 0, that means if the value of f at c is equal to 0, then the theorem is proved. If not, if f of is, that means f of c not equal to 0, then it must be less than 0 or greater than 0. Is it not? So if f of c not equal to 0, it means be less than 0 or f of c greater than 0. If f of c, let me take f of c greater than 0 in this interval and f of c less than 0 in this interval. Let me take this c as c1, this a as a1 and b as b1. Previously a comma b I took as a1 b1. So when I took a1 b1, between it is c1 a1 b1, it is c1. Since f of c1 not equal to 0, I will check is f of c 0 in this interval or in this interval, any one of these intervals. If I took these intervals, again I took the midpoint of this. Let me take this a1 c1 interval as a2 b2, whatever it may be. If this side or this side, whatever it may be, took a2 b2. The midpoint is c2. Again I will check if f of c2 is equal to 0, then the theorem is proved. Otherwise f of c2 less than 0 or f of c2 greater than 0. So again I take this as two parts. So this will be a1, this will be c3. Okay, so like this I continue until I found the c which for which f of c is equal to 0. So here for first interval I took I1 a1 a2, f of c1 not equal to 0. Then I took I2 which is a2 b2, in which is I2 is contains in I1. See, this is I1 interval, this is I2 interval. So I2 interval is subset of I1 interval. Like that I will continue up to IR intervals where f of CR is equal to 0. If f of CR not equal to 0, again I will follow the same rule again until that C is found. See this. So now proof, as I explained previously, let f is continuous on a comma b and f of a, f of b have opposite sides. That is, f of a less than 0 and f of b greater than 0, or f of a greater than 0 and f of b less than 0. Let me take case 1 as f of a less than 0 and f of b greater than 0. That means f of a is less than 0, that is less than f of b. So I took I1 is equal to A1 B1, that is equal to A comma B. Let C1 is equal to A1 plus B1 by 2 be the midpoint of I1 interval. If f of C1 is equal to 0, then C is equal to C1 and the theorem is proved. What I explained previously. If f of C1 not equal to 0, then either f of C1 greater than 0 or f of C1 less than 0. If f of C1 greater than 0, we take A2 B2 as A1 C1, while if f of C1 less than 0, we take A2 B2 as C1 B1. In either case, we have I2 is equal to A2 B2, which is contained in I1. And as usually, f of a less than 0 we took there, no? Like that, for this interval A2 B2, f of A2 less than 0, f of B2 greater than 0. This is case 1, no? By continuing the bisection process, suppose that the intervals, by continuing above process same as it is, I2, I1, I2, so on IR, that will be in the form of IR contains in IR minus 1, contains and so on, contains in I2, contains in I1. These I2, so on, IR are the subsets of I1. First I1 is A comma B, have been continued in the same manner successively. For IR is equal to the interval AR, BR, we will have f of AR less than 0, comma f of BR greater than 0. If CR is equal to AR plus BR by 2 is the middle point of IR, and if f of CR is equal to 0, then C is equal to CR and the theorem is proved. Otherwise, we take IR plus 1 is equal to, next interval we will take IR plus 1 is equal to AR plus 1 comma BR plus 1, and f of AR plus 1 less than 0 comma f of BR plus 1 greater than 0. If the process terminates by finding a point Cn such that f of Cn is equal to 0, then the theorem is proved for C is equal to Cn. Otherwise, we apply the sequence of nested intervals. In is equal to An comma Bn, L belongs to capital N, with f of An less than 0 and f of Bn greater than 0. Also, length of In is equal to B minus A by 2 power n minus 1. By nested intervals theorem, there exists a point C belongs to In for all n belongs to n. Since C belongs to An comma Bn, that implies An less than or equal to C less than or equal to Bn for all n belongs to capital N. Because C belongs to An. C is in that interval An comma Bn. That implies 0 less than or equal to C minus An comma Bn minus C less than or equal to Bn minus An. Bn minus An is equal to B minus A 2 power n minus 1. By squeeze theorem or sandwich theorem, limit An is equal to C, that is equal to limit Bn. Since f is continuous at C, we have limit f of An is equal to f of C, that is equal to limit f of Bn. So f of An less than 0 for all n belongs to n, that implies f of C is equal to limit f of An less than or equal to 0. F of Bn greater than 0 for all n belongs to n, that implies f of C is equal to limit f of Bn greater than or equal to 0, hence f is equal to 0. So, if f is continuous and f of A and f of B have opposite signs, then there exists a point C belongs to A comma B such that f of C is equal to 0. Now let us take a second case. In first case we took f of a less than 0 and f of b greater than 0. Now in second case we took let f of a greater than 0 and f of b less than 0 such that f of b less than 0 less than f of a. Define capital F a comma b to R such that f of x is equal to minus f of x for all x belongs to a comma b. Then f of a is equal to minus f of a, small f of a, f of b is equal to minus f of b such that f of a less than 0 less than f of b, which is in case 1 condition. So f is continuous on a comma b, that means capital F is also continuous on a comma b. By case 1 there exists c belongs to a comma b such that capital F of c is equal to 0, that implies minus f of c is equal to 0, that is f of c is equal to 0. Here it's the two theorems. Thank you.